All right. So for this part of the iOS decal, we're coming into the final stretch of the class. And as I hope you realize now, we are in final project mode. And that means all of you should really be putting in time onto making your final projects. And everything that we teach you in this class should be right now geared towards helping you prepare for those final projects. So with that in mind, instead of doing lecture normally, where we go over some more maybe theoretical concepts, I'm going to go over a series of more specific tutorials on more specific iOS libraries and SDKs that might help you in your project. So for example, in this demo here, I'm going to go over a SpriteKit demo. And instead of just coming up with one completely from scratch, I wanted to have you guys have some type of resources like reading resources and code resources along with the demo. So I'm actually just going to follow along with demos that already exist online so that they're easily accessible by everyone in the class. This demo is from Ray Wenderlich. I expect many of the demos that I'm going to be doing for the rest of the semester will be by this guy or on this website. This is an awesome resource for iOS demos. Everything is free on the website. They also have some premium content as well, but basically this is probably the single best iOS tutorial site that I've ever found. So for this tutorial, we're going to be going over SpriteKit. And SpriteKit is really for if you want to make a game in iOS, and specifically a 2D game. So more complex things like a 3D game with, or an AR game, something like that, that would not be SpriteKit. But if you wanted to make, a simple platformer or a, simple 2D shoot 'em up game, then SpriteKit would be the tool for you. So to start, I downloaded the starter code here. I'm also going to link this starter code on the website, so you don't have to make an account to download it. And if you scroll down, blah, 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 you can also see there's another very popular game engine in general is Unity. And Unity is really, really powerful because it allows you to create cross-platform gaming experiences. So if you were, a legit game developer and you wanted to do some really powerful, fancy things, you'd probably want to use Unity. But SpriteKit for complete beginners, as it goes over in here, SpriteKit's a lot easier to use. It uses all iOS native tools, and you won't have to learn a completely new framework and a completely new way of building applications because Unity requires that you know that kind of stuff. Anyways, if you have experience with Unity, I would highly encourage you to use that because it does have iOS compatibility. But anyways, moving on. For SpriteKit, getting started with our SpriteKit app, this is going to be true of pretty much every SpriteKit app that you make. You're going to go ahead and have something like this in your view did load. Essentially what this is doing line by line, one, it's creating this game scene, which is sort of like a view, but it's more of like the content of a view. And this is going to be where we're going to add all of our sprites to this scene. And we also want to attach the scene to a view. And that view is going to be of type SKView. SKView stands for SpriteKit View. And right here, what this line is doing is it's actually casting the view, which is basically the view in our view controller, as a SKView or as a SpriteKit view. Let me just copy this in to the actual starter code, which I have right here, and maybe this will make a little more sense. So again, we got our scene now, which is our SpriteKit scene. You can see we've imported SpriteKit here at the top of this game view controller already. You also might want to notice this view here, or the view controller, we have nothing in it at all. So you can start with a completely blank screen here, and we're essentially going to programmatically add all the stuff we need. This size, views.bounds.size, that's going to be the size of the actual view. Again, this view is referencing basically this big white screen in the background of our view controller. We can always reference this sort of background screen by in our view controller class right here, just with the keyword view. So anyways, this is making our background white screen a SpriteKit view. And then this just shows a little frames per second stat at the bottom. This is more for testing purposes, but you don't really need that. Same with the shows node count. It shows how many nodes are on the screen. This is also not really needed. Ignores sibling order is just a optimization you can use if you don't really care about the order in which the nodes are presented, if they're overlapping or not. Don't have to worry about it, but you can look this up if you want to learn more about it. But basically, it just makes it run a little bit faster. Scene.scale mode equals .resize fill. This might look familiar from sort of like the image view stats that we could do, like the image view setting the scale mode to aspect fill or aspect fit. This is very similar. And this is actually a pretty similar interaction here. This scene you can sort of think of as your UI image, and this SK view you could sort of think of as your UI image view. So remember, you have to have a UI image view, and in that view you put an image. Similar relationship here between the SpriteKit view and the game scene here. All right. So at the very end, we have present scene, skview.present scene, and we put in our actual SpriteKit scene here, and that will actually make our view display our scene, which is basically where all of this stuff is going to take place. Okay, so back to the tutorial. So now to actually add a sprite, we're going to go into gamescene.swift. So we'll copy all of this over, and gamescene.swift is this file here. And you can notice this is actually what we created here, this game scene. This is actually a custom class that we wrote, and it's just of type skScene. And so anything of type skScene you can use as your scene for the view here. Okay, so let's paste in the code that they wanted us to paste. Ooh, I forgot the L. All right, so what is this doing? So first, it is actually creating a node for our player. Again, in this game, if you didn't realize this, we're actually basically creating a little ninja, and there's going to be little enemies that fly across the screen, and our ninja has to throw little ninja stars to kill our little enemies. And so this player is going to be our ninja. It's going to be an skSprite node, and it's going to take in an image, and it's going to be an image named player. So if we go to our assets folders here, we can see there's a bunch of assets that they've included for us in the starter code. And player, this is our little ninja guy. So that is really useful. And we can just create a SpriteKit node out of that with this line here. Now there is a function that is part of the skScene class that we can override called didMove. And this you can sort of think of as the viewDidLoad for this SpriteKit scene. So this will be called right when this scene is about to be presented. And basically here we're just doing some setup. So we're setting the background color for our scene to be this SpriteKit color.white. A lot of this stuff in SpriteKit is going to actually need to use SpriteKit colors instead of UI colors. You notice we're not actually using UIKit here. So, in our view controller, we always need to import UIKit to get UI view controller. UIKit also includes, UI views, UI image views, UI colors. SpriteKit is going to be a whole different world. So we're going to have to basically play by SpriteKit's rules here. So SpriteKit has its own color class. Then we're going to set the position for our sprite node, which is essentially going to be a coordinate point, like an X and Y coordinate point. You can also set a Z coordinate, but that only determines how these nodes are overlapping. Because remember, we are only working in a 2D world with SpriteKit. So we're going to set an X and a Y coordinate here. And what this position represents is we want our player to be in the middle of the screen. So that's the Y coordinate is going to be size.height times 0.5. Size is going to be one of the properties of our game scene. So essentially we want this guy to be halfway up the screen vertically. and we want it towards the left-hand side of the screen. You notice our x-coordinate is the width of the screen times 0.1, so we want it sort of a tenth of the way from the left-hand side of the screen. So that's going to set the center coordinate for our player, and then the last line that we need to actually add this node to the screen is add child of player. So if we run this real quick, we can sort of see what this means. So here you notice we have our little ninja guy about a tenth from the left-hand side of the screen and centered vertically. So that is exactly what we want. You also notice that the phone is horizontal by default. And if you notice, if we try to rotate it, so if we try to rotate the screen like vertical like this, nothing rotates. And the reason for that is you can go into the project settings here, so this little blue line here, and you guys have worked with these before, but one of the settings that you can set are the device orientation settings. So you can just, in this case, lock it to be either landscape left or landscape right. So it doesn't allow it to be vertical or upside down. Just another little tidbit. Okay, and so now we have our guy. He is centered as we want him to be. Now we actually need to have some enemies. So going back to the tutorial, let's scroll down and you can see we have our guy, moving monsters. So this is what we want. So we're gonna add these methods to our game scene.swift file. And we go back here, go back to game scene.swift, and let's take a look at these. All right, so basically they've written this weird random function. I'm not a huge fan of this, but just take it for what it is. But the important thing is that this random function takes or returns a CG float. And CG floats are really important because this basically stands for core graphics float. And this is going to be the type of number that we have to use when referencing actual screen coordinates. So you noticed here for the position, we had a CG point. That was the type of XY coordinate point that we made. For single values, we're going to actually need CG floats. So each of these values will actually be converted into a CG float also. We also created a random function between a certain range that just, again, gives us a random number between the minimum and the maximum. And now this is sort of the more SpriteKit related stuff. We have this function called add monster. So the first line is going to create a monster. It's going to be an SKSprite node with the image named monster. And again, we could see our monster in our assets folder, this little ghost guy. And next we want to determine where to actually spawn the monster along the y-axis. And this is where our random function comes in between this min and this max value. So the y coordinate point, again, this needs to be a CG float. This can't be a normal float or a normal integer. So this random function will guarantee that we get a CG float, and that value is going to be between the bottom of the screen and the top of the screen. The bottom coordinate would be the CG float 0, and the top coordinate would be the size.height. But you notice that instead of just creating it at the bottom or between the bottom and the top, we add this little monster.size.height term. And that's because this coordinate point is going to be the center point of this monster or of this SpriteKit node. So if the center point could be at the 0 coordinate, then you can imagine half of the monster would be cut off at the bottom. And similarly at the top, if we had this max as the just size.height, then half of the top half of the monster might be cut off if it's all the way at the top. So we actually constrain the range where this monster can be by or in relation to the actual height of the monster. Now it's time to actually decide the initial position for the monster. And that is going to be basically we're just going to construct this based on this actual y. So you can see this y coordinate would be this actual y here. And the x coordinate is actually going to be slightly off the right-hand side of the screen. And so to do that, we do the size.width for the x-coordinate. So again, that'll give us all the way to the right part of the screen. Again, if we just said size.width, then that's the middle coordinate. So the width of the monster might make it slightly overlap and start a little bit onto the screen. So to make sure it's all the way off the screen, we add this monster.size.width over 2 to this x-coordinate. And finally, just like adding our player, we want to add a child node for this monster. And this add child method, I should have mentioned, is just a built-in method of the skScene class. So we can just call it and it'll automatically add this node right to the screen. Now, how about actually animating these monsters? So we've created them, they're slightly off the screen to the right, or we've created one at least. Then now we need to have it move from the right-hand side of the screen all the way over to the left-hand side of the screen. So to do that, first we're going to determine the speed of the monster. We're also going to have these monsters come out at different speeds. And this speed is actually going to be a time here. So that might be a little misleading. Basically, the duration of that animation is obviously going to then translate to the speed. So the duration is either going to be, or it's going to be between 2 and 4. So it's going to be between 2 and 4 seconds for the monster to go from the right-hand side to the left-hand side. And now we actually add our animation, which in SpriteKit are called actions. So to create one of these move actions, so move from the right-hand screen to the left-hand side of the screen, then we could create this skaction.move to, and the point that we want to move to is going to be, again, that's going to be the point on the left-hand side of the screen, so just off the screen to the left. And so in this case, we keep the y coordinate the same. So these monsters are going to move straight flat across the screen. And the x coordinate is going to be just off the left-hand side. So in this case, that's going to be the monster.size.width over 2, but the negative of that. So basically a little bit more than the furthest left-hand point. And being able to specify these coordinates as, off the screen is really useful, because then we can make sure, our monster actually goes all the way off the screen and isn't just hanging on right on the side. The next argument, this kind of got messed up when I pasted it, but this is the duration of our SK action. Then that is going to be, it's going to be of this type time interval, and you could pass in just a CG float as the time interval. So that's going to be this duration that we chose here. Next, we have this action move done. So this is basically going to be the action that is when this action is completed. We're going to make that the skaction.remove from parent, which essentially just removes the node altogether. So it deletes it. And now to actually run this action, so basically what we want to do is run this action move on our monster. And when it's done, we want to call this action move done. So we can just use this really handy thing called skaction.sequence. We just pass in an array of actions that happen one after another. So where our sequence is going to be action move, it's going to complete this. And if it completes this action, then it'll run this action move done, which then removes the node altogether. And again, this is all wrapped in within this monster.run call. This .run method is on any SpriteKit nodes, and it takes in a SpriteKit action. Great. All right, so that is going to actually animate some monsters, or at least a monster. We could just run this to run, or have one monster come across the screen. So let's call add monster, and we'll run this. And you can see now we have this one monster come flying across the screen, and that's exactly the expected behavior. But we don't just want one monster to come across the screen, we want a bunch of monsters to come flying across the screen. So let's go back to our handy tutorial. So if we keep scrolling down, this next code block here The following code we need to add to the end of this did move to. So again, that's sort of like our view did load for our scene. So here I'm going to delete this add monster. I'm going to paste this in. So this is a method that essentially is just going to keep adding monsters over and over again. And the way that we're going to do that, so just like our SK nodes or SK actions had this run method, our game scene also has this run method. And so we can pass in this repeat forever action. So basically it's just going to say keep doing this action forever. And within this repeat forever action, we can put a sequence. And that sequence is going to be running this add monster call. So it's going to, again, obviously run add monster over and over again. And then it's going to wait for 1 second. So this is a really clean way of creating, it's called a game loop. And there are other, things you could repeat for a certain amount of times. You could repeat until a condition is met. In this case, we're just going to have it go forever for now. And now if we run it, we can see we have many monsters flying across the screen. And you can see there's also a random Y position at which they appear. And you can also notice that some of them are moving at different speeds. Cool, that is what we want. But this game is not very exciting if we cannot actually try to beat these monsters. So let's go ahead and see what is next for us. So shooting projectiles. So you notice here we're going to need a little bit of trigonometry. And the way that this trigonometry is going to work is we're going to get this touch as a coordinate point. And we also, again, we have the position of our little ninja already set. So we need to, instead of just moving, this ninja star straight to this touch point, we need to make sure that it moves through the touch point off the screen. And we also want to make sure that this distance, this hypotenuse, no matter where the touch is on the screen, we want this hypotenuse to be the same length. And that's because when we create our action that's going to actually move our ninja star, we want it to be the same speed no matter where we touch. And so the speed is a function of the time and the distance that we're moving it. So we set the time to be a constant time, as you remember, moving our little ghost enemies. And if we set the distance here to be a constant distance, then everything will work out and our ninja star will move at a constant speed. And the actual trigonometry that we're going to have to do here, you probably noticed this looks like a problem from like high school or even maybe middle school, where we have this angle here, and that's going to be the same angle as this angle here. We find this angle using the a tangent of the y, or opposite over adjacent, and then we can take the cosine of that angle times our hypotenuse and then find the big base here, or we can take the sine of our angle times the hypotenuse and get this side here. So let's go ahead and implement that real quick. So first of all, we're going to, I also want to mention, we're not going to use the method that they used. They, I think, did a lot of extra work in order to create some vector arithmetic. And the way they did it was they treated this touch as a vector, like with an x and a y point. They normalized that vector, and then they actually multiplied it then by a constant, so basically scaled the vector to a set length. Same effect, but they ended up doing a lot of extra work that I don't think you really need. So what you really need here is, first we're going to want to actually override a function that is in a lot of different classes in iOS development, and that is there's touches began as well as touches ended. And so in this case, let's actually use touches ended. This is actually the more conventional approach, and that's because you can imagine when you're tapping on a button in an app, generally you expect that button isn't activated until you actually let go of that touch. You can imagine clicking on a button you didn't mean to, swiping your finger off that button while still holding on, and then letting go off the button. It doesn't actually trigger the button. It's just a convention that you've probably gotten used to and that didn't even realize it. But we're gonna use touches ended, which is gonna be called as soon as a touch stops on our SpriteKit view. And in order to actually get the UI touch object here, we're gonna go guard let touch equals touches, which is a set of UI touches, and we just want the first one here. There should only be one touch when touches ended is called. And then if there's no touch, or sorry, if there's no first touch, then we'll just return out. And then we can get the location of the touch by calling touch.location. And this location is going to be a CG point, so that X and Y coordinate point that we used earlier, but it's going to be relative to whatever we put in here. If we want it to be the XY point of the whole screen, then we could just put self in here. Remember, self is this SK scene, which takes up the whole screen. So this will give us like the meta coordinate points. But if you, for example, had like a little sub view in an app and the app didn't take up the whole screen, then you might want to get the location relative to some other point. Anyways, we're going to go ahead and get the location like that. Then we're going to want to get the base of this triangle and the height of this triangle. So this X offset and this Y offset. So I'm going to say let base. The base is going to equal this location's X point minus this guy's X point. And remember, 0 is the farthest left. So that's like the 0 X coordinate, and the 0 Y coordinate is at the bottom. So if we just do location.x, that's our touch location, minus our player.position.x, that should be the base length. And remember, we made a reference to our little ninja player right here. Great. And now for the height, it's going to be pretty similar. Let height equal location.y minus player.position.y. Cool. And now we're going to want to actually get this little angle here so we can do our trigonometry. And that angle, hopefully you remember from your trigonometry classes, it's going to be the A or arc tangent of the opposite over the adjacent. So our, in this case, height over base. So we can let angle equal A tangent of our height over our base. Cool. And then now let's actually get this like big hypotenuse length. So I'm going to say let big hypotenuse equal, and again, this is going to be a constant length. We want this hypotenuse to be the same no matter where we touch. So let's just make it the width of the screen so we can guarantee that it definitely extends off the screen in every direction. So we can go ahead and do size dot width. Cool. So that'll be our big hypotenuse length. Let's let our big triangle height is now going to equal the sine of this angle times the times the hypotenuse here. So sine is opposite over hypotenuse. So sine times hypotenuse will equal opposite. Big height is going to equal sine of our angle times our big hypotenuse. And similarly, let big width or big base, keep it consistent, going to be the cosine of our angle times the big hypotenuse. Great. Now we want one of the restrictions that it says in this spec online is that we don't want the ninja to be able to shoot behind himself. So to check that, we can just check whether this base, this offset X, is positive. So if it's not positive, if base is less than or equal to 0, then we can go ahead and just return, do nothing. If it's greater than or equal to 0, then let's let our ninja star equal, and if we go into our assets here, we can see we have this image called projectile. That's our little ninja star. So we can go ahead and set a new SK sprite node from an image named projectile. Cool. And then we can set the position. Remember, the initial position of our ninja star should probably be where our ninja starts. So we can say ninja star.position equals the player.position. So now we're going to need the actual destination coordinates here. And we can actually make the destination coordinates relative to our ninja here by adding this as a child of the ninja itself. So that'll make the coordinates all relative to the ninja, which is going to be useful because then we could just use this height and this base as our coordinates. So we can go ahead and say let final position, it's just going to equal a CG point with our our X is going to be equal to our big base, and our Y is going to be equal to our big height. Great, and now we're going to want to have an action to move this thing, just like we did for the monster. So I'm just going to copy that over and copy the action move as well. Oops. Cool, and so this action move, instead of moving to this coordinate point, it's going to move to our final position, and the duration, let's just make it 2 seconds each time. Sweet, and the action move done, same thing, we're going to remove from parent, and then instead of monster.run this sequence, we're going to have our ninja star.run this sequence. But before we can actually run any actions, we're going to want to make sure that I'll put this here, that we actually add this ninja star as a child. So if we add this ninja star, if we just use this add child function, that's going to add it as a child of the sort of super node, the actual scene itself. But we could, again, in order to translate our coordinate system to be relative to our ninja here, instead of making that the 0, 0 point, this will be the 0, 0 point. We can add it as a child of the ninja. So let's do ninja player dot add child, and it's going to be ninja star. And it looks like we forgot a close bracket. And now this should throw some ninja stars. So let's go ahead and run it. And here we have our little ghost flying across the screen. And I actually realized I made a mistake. Right now, the ninja stars are flying from the top of the screen. And the reason for that is because if we want to translate the coordinate system to be make the 0, 0 point where the player is, the actual position of our ninja star, our initial position, shouldn't be the player's position. It should actually be a CG point should have a dot 0. Yep. So it should be just the 0, 0 point. So if we go ahead and run this again, this should work. And sure enough, here we have our ghost flying across the screen. You can notice our ninja stars move perfectly through the cursor when we click. That looks really nice. But we cannot kill our ghosts yet because we have not implemented anything about our ninja stars intersecting with these ghosts. So let's go ahead and do that next. So there are several ways to detect whether certain objects overlap in SpriteKit. The way that the tutorial goes over in the linked tutorial, that has you actually implement these physics bodies that are attached to your SpriteKit nodes. And these are really cool and really powerful. They allow you to do really complex things like have an effective gravity on certain nodes as they fly across the screen, enact different forces on different nodes in different scenarios, and also have the nodes collide in certain ways and have them, the physics of their collisions actually make sense. In our cases, we don't really need all those complicated physics objects. And the way that the tutorial uses them is you can also use these physics objects to detect collisions. We're not going to do it that way. There's another way to detect whether certain nodes are overlapping, and we're going to go ahead and do that. To do that, we're going to go ahead and override a function called update. If you just write func update, it should autofill like this. And this is actually called every single frame of our scene. So every single individual frame will call this function before actually rendering that frame. So basically this is called over and over and over again a million times, which is really useful for us, but we also want to make sure we don't do anything too expensive in this update function because it's called so frequently. In our cases, our app is pretty simple in this case, so we should be able to add some stuff here without worrying about it. First of all, let's go ahead and get a reference to all of our ninja stars on the screen. To do that, we're going to say that ninja stars equal. You can see we had all of these ninja stars added as children to this player node. And to get a reference to all of the current children that are there, we can simply go player.children. And all the ninja stars, or all of the children nodes of this player are going to be ninja stars because we didn't add anything else as a child to the player. But for the actual monsters, in order to get references to them, unfortunately, we also have this player that was added as a child of the root node, and the monsters, again, were also added as children of the root node. We can go ahead and put self here just to reinforce that. This is adding the children to the SK scene itself. So we're going to have to filter out the monsters from our little player node. To do that, we can go ahead and give a name to these different nodes. Let's go ahead and just set player.name, right before the add child, player.name equal ninja. Cool. And now we can also go ahead and just for child in self.children, it's going to be a bunch of SK nodes. If child.name doesn't equal ninja, that means we have a reference to a monster node here. And when we have a reference to a monster node, we want to check if it overlaps with one of our ninja stars. So now we can iterate across our ninja stars for star in ninja stars. If our child dot intersects, so this is a method of these SK nodes, intersects, and you can see if it intersects with another node. So if it does with the star, then we know now there's a collision taking place. So if we had some game logic, like update game logic here, like maybe increase the score, because that means that one of our stars connected with a ghost. But in our case, all we're going to do is remove both the star and the monster that was on the screen. And to do that, we can simply go child.remove from parent and star.remove from parent. Nice. So pretty nested here. I probably could clean this up, but for our purposes, this should be sufficient. Let's check it out. We got our ghosts flying across the screen, but now if we have a well-timed ninja star, we notice that both the ninja star and the ghost disappear just like we want. Now the last part of this app is actually detecting when a ghost gets off the screen. So there's kind of two ways we could do this. One is we could create an a giant invisible node right here and detect whether one of these ghosts collide with that invisible node, just like we did with the ninja star. Another kind of interesting way of doing this, though, is we remember we had this series of actions for our ghost right here, or for our monster. We had it actually execute this action move, which moves it across the screen, and this action move done function here, which removes the SK or the node from the parent. So it actually makes it disappear. We can actually add another action here, and that can be to call a function. So function, say monster made it to end. I don't know, something like that. That's not a very good name, but regardless, we could have this function here. We could print, oh no, you lost, something like that. And in here, we probably realistically would want to implement some game logic or update some game state. So, however you wanted to handle a ghost making to the end, whether that's making a game over state or whether that's making you lose points, however you want to implement that. And we can call this function by simply going skaction.run and monster made it to end. And now this will be a series of 3 actions. But you might be wondering, well, if our monster gets killed by our ninja star, won't it still run these other 2 actions? It doesn't. So if a node is removed from the parent node before all the actions are completed, it doesn't actually run those sequential actions. So this will only be called if the monster actually makes it to the end of the screen. We can go ahead and run this one last time. And we can still kill these monsters here. And if we look here, nothing's been printed. And now, oh no, you lost. And we can get that printed multiple times as more ghosts make it across the screen. So for the sampler lab for this week, we're going to have you make your own SpriteKit project. Again, sampler labs are optional. They are worth 1 extra credit point. But this sampler lab will basically have you implement, it could be this same exact game, but instead of just having these print statements, you should have an actual game state and actually have a score and a game over state. So to repeat that, for the sampler lab, you're going to implement a game. It can be just this exact game, but the game will need to have a game over state as well as a score. So go ahead and do that if you need some extra points or if you want some more practice with SpriteKit.